theorem of Algebra theory. I will state it again and then finish the proof. So we have the fundamental theorem of Algebra theory. So, as we said, so L over K is a Galois extension. And then we have bijections. So there are inverse bijections. So we have from the subgroups of the Galois group with the intermediate fields of L over K. Where is this? Okay, here. Of L over K. And so in this direction we have that group, what do I want to call it? The group is so group H is set to the fixed field of H. So this is the set of all elements in L which are invariant of all elements in H, and to an intermediate field F we associate the Galois group of L over this intermediate field. So that these two are inverse to each other and therefore bijections. This just means that if we take, say, the Galois group of L over the fixed field of a subgroup H, this is H for any subgroup of the Galois group, and if we take the fixed field of the Galois group of L over some intermediate field F, this will be F. Here this is for all H, subgroup of the Galois group, and this was for all intermediate fields. So this, so we have proven this, and there were, so this is somehow the main part. There's some simple numerical consequences which we will now prove, so that we take the degree of L over the fixed field of some intermediate, some subgroup. This is equal to the order of the subgroup H, and the degree of the fixed field of H over K is equal to the index of inside the Galois group of L over K of H. So for all H in this, for all subgroups. And similarly, well, if I write here, so the degree of L over the intermediate field is equal to the number of elements in the Galois group of L over F. So the order of this group, and index also the degree of f over k is equal to the index in the Galois group of L over k of the Galois group of L over f. So the index. Can I actually read it? It's a bit too high for me. So maybe here I draw the line. So for all f intermediate field. Okay, proof. Well, in some sense, these two statements, this one and this one, are almost twice the same. I mean, twice the same statement, stated in a slightly different way. So we have shown one, and now we want to show this simple consequence here. So we have to do the select let H in Galois group of L of K subgroup. Let F be the fixed field of the subgroup. So some intermediate field. So we know, we have seen before in the proof, but it's anyway almost obvious that the field extension L over F is a Galois extension. Well, we know that for any intermediate field, we get the big field over the intermediate field is Galois. So thus, the degree of the field extension is equal to the number of elements in the Galois, to the order of the Galois. So this is this statement here. And we also have, as in this Galois group, and the Galois group we had said that the Galois group of L over the fixed field of is equal to H. No, this was part of the statement of the fundamental of Galois theory. And and we have obviously that L over F by the degree theorem times the degree of F over K is equal to the degree of L over K. And so thus we just divide this by this. So it follows that the degree of F over K is equal to the degree of what is it? L over K divided by the degree of L of what is it? L of L over F, which is the order of the Galois group of L over K divided by this, what we had here, and this is the same as the index of H in this thing. So basically, just by definition, this holds. Maybe these things I can leave to you as an exercise. It's basically the same kind of level as, I mean, it's more or less the same. It's quite trivial. So the rest is similar. Anyway, you can see that the actual thing to prove is this, and these are just simple observations. So we have this we now have this 1-1 correspondence. Which I just wipe it out to write again. So we have this 1-1 correspondence. Between the subgroups of the Algebra group of L over K. So, and the intermediate fields. So for a Algebra extension. Now, we can ask ourselves whether we can get some finer information. For instance, if we have a particularly nice subgroup, does it tell us something about having particularly nice intermediate fields? Or if we have particularly nice intermediate fields, do they correspond to particularly nice subgroups? So, I mean, there are not so many notions of nice that we know. We only know, so that we have one notion of subgroups that are better than others, that are normal subgroups. And so, what kind of intermediate fields correspond to normal subgroups? What kind of and or we also know some other nice intermediate field. We could have that this intermediate field f over k itself is a normal extension. So what subgroups? What kind of subgroups? Correspond to f, intermediate field, with f over k. No. So by some remarkable coincidence, we have here twice the same word, and so therefore the natural conjecture is that these two statements should be equivalent. So that the intermediate field is normal if and only if the corresponding subgroup is normal. Obviously, the history, I mean, it's clear that this is not a coincidence. So the group theory originally was invented to do Galois theory. And so originally one introduced normal field extensions, and the condition on the, and then one wanted to relate this field extension to the corresponding intermediate fields. So a subgroup was called a normal subgroup if and only if the corresponding field extension was normal. And so that's how history goes. Nowadays, one normally thinks that group theory in some sense is more basic than field theory, but this is the original way how it went. And so, so now let's, so therefore we want to obtain that, so we want to show that H subset Algebra group of L is a normal subgroup if and only the fixed field of H in L. So the fixed field of H, which is a subfield of L over K, is a normal extension. So we know the other way around, it's always true. No, that we had seen that if we have that L over the fixed field, actually L over any intermediate field is always a normal extension, but almost by definition. But to have it the other way around is not so clear. Okay, so let's now go about doing this. And so we can so there, because we find there's also another description what it means to be, for this to be normal, which is also kind of nice. So you can first look at the following situation. So let's assume f in so let f be an intermediate field of the Galois extension. L over k, and assume, let us take an element alpha in the Galois group of L over k. So if it's not an element, so we can ask ourselves, what does this to elements in F? Or we could ask us more generally, does this map F into itself? So if it is an element in the Galois group of L over F, then it will map every element of F to itself. But we could also ask ourselves just whether it sends F to itself. So, but anyway, so we put alpha of F to be just, the image. So this is just a set of all alpha of B with B an element of F. And now you can, it's immediate to see that this is also an intermediate field. Alpha of F is an intermediate field. Of L over K. Because obviously, it's a subset of L. It contains K because alpha is the identity on K. And it's a field because this is a field homomorphism, this alpha. So if I take the product or the sum of these elements, it will be of the same form. Okay. So now we want to see, for instance, how does the Galois group so we have the Galois group of L over F, and we have the Galois group of L over alpha F. How are they related? And that's very easy to see. So F intermediate field of the Galois extension L over K. And we take again alpha, an element in the Galois group of the big extension, then the Galois group of F over alpha of F. Well, what can it be? It should be somehow having to do. So I claim this is alpha, the Galois group of L over F, alpha to the minus 1, which I mean is the set of all alpha phi alpha to the minus 1, where phi is in the Galois of L over F. So if we move F by an element in the Galois group, the Galois group of the, this corresponding group gets conjugated by that element. And this is almost trivial. You just have to write down what it means. So if I take an element phi in the Galois group of L over F, no, first I take any element phi in the Galois group of L over K. So I know that an element in this Galois group here is in particular an element here. Meaning it's the element in the Galois group of L over K, which is the identity on alpha F. So then phi is in the Galois group of L over alpha of F, if and only if, by definition, for all elements A in F, we have that phi of alpha of F of A is equal to alpha of A. No? So it just means that is the identity on alpha of F. So, which is equivalent to saying that alpha to the minus 1 phi alpha is an element in the Galois group of L over F. No, because alpha to the minus 1 phi alpha, according to this, if you multiply by alpha to the minus 1, it sends A to A for all A. And so if I put this back, so phi is in this Galois group if and only if it's of this form. I can multiply back by alpha here, by alpha to the minus 1 here. So it follows thus phi is in the Galois group of L over alpha of F if and only if phi is an element in alpha the Galois group of L over alpha to the minus 1. And we just multiply like this. What?
Yeah, I mean the inverse.
What inverse?
No, I mean instead of multiplying the inverse of this is in the group because this is a group.
What? So I have not understood.
No, I was thinking like instead of multiplying, the inverse of this element should be in the group again. So that's why we can exchange the inverse in there.
Maybe, but I mean, here I just want to say if I have this element, so this element is in the, so phi lies here. So it means if I multiply, so no, this element lies here for every phi. So now we can instead multiply with the inverse of this, on this side with the inverse of this. Then it means that our phi was lying here. No, that's just what I do. I mean, I just have taken this identity and multiplied it by alpha on this side, by alpha to the minus 1 on the other. Okay. So you see, it's essentially by definition this is true. But so then, using this, we can see what happens. I mean, in particular, this statement here will follow from this if we, and we also see that it is related to another nice property. This is so on theorem. So we have L over K is the Galois extension. Then the following are equivalent. So first, and that's F in intermediate field. So first, F over K is normal. The second statement, as one can also see here, is that if I take this alpha of F this is equal to f for all alpha in the Galois group of L over K. So we know that the elements which fix every element of F are just the elements in the Galois group of L over F. But nothing prevents, it could happen that every element of F is set to some possibly different element of F. And we claim this is true if and only if F is normal over K. And the third one is what I said, that the Galois group of L over F is a normal subgroup. Of the Galois group of L over K. Okay. So we have to show that all these three things are equivalent. So let's start going from 1 to 2. So we assume that F over K is normal. And we will want to show that every element in the Galois group of L over K sends it to itself. So let's take any element A in F and let F be the minimal polynomial of A over K. So as this is a normal extension, we know, so this F is an irreducible polynomial over K, which has a 0 in F. So it splits over F into linear factors. So as F is normal over K, so all roots of the polynomial F in L lie in F, because F already split, so the polynomial F already splits over F. So, and so all the roots lie in the small field F. So now we use our standard trick that alpha be an element in the Galois group of L over K. Then we can apply alpha to this root A, and we'll see it's again a 0 of F, by the same old trick. Then alpha of A is also the root of F. Because as we have seen many times, we have that 0 is equal to f of A, which is also alpha of f of A, and this is equal to f alpha of A. So, therefore, we have seen that this polynomial already splits over f, so therefore it follows that alpha of A is in F. And that's it. So this kind of trick works very nicely. Okay, so now we come. So, well, strictly speaking, I mean, we might maybe, to make it complete, we want to say, so thus, we have in a moment just shown that alpha of f is contained in f. But obviously we can apply the same with alpha to the minus 1. So, same argument with alpha to the minus 1 gives f is contained in alpha. The operator gives that alpha to the minus 1 of f is contained in f, and then we multiply with alpha, and so they. So now we go from 2 to 3. So we assume this statement, and we want to show this is a normal subgroup. That's almost obvious by the lemma we just proved. So we assume 2. So that is alpha f is equal to f. For all alpha in the Galois group of L over K. Then, so let's take such an alpha. And then we have seen that if I take the Galois group of L over alpha of F, we had seen that this is equal to, which one was alpha, the Galois group of L over F, alpha to the minus 1. On the other hand, we have, our statement is that F is equal to alpha of F. So this is equal to the Galois group of L over F. And this precisely says that this is a normal subgroup. And finally, we have to go back. So actually, we don't get any presence here. So basically, going back is that we first go from 3 to 2 and then from 2 to 1. So it's not like there's a shortcut by going around. And this is also the slightly more difficult statement. And in that, we have to use the fundamental theorem of Galois. It's not very difficult. So let's assume that the Galois group of L over F is a normal subgroup. Of the Galois group of L over K. So then we will have to show these statements. Hope you will remember, so we will have to eventually show that f over k is normal. Basically, we kind of start by more or less retracing our steps. So let alpha be an element in the Galois group of L over K. Then we know that the Galois group of L over F is again equal to the alpha, the Galois group of L over F alpha to the minus 1, because we have assumed that it's a normal subgroup which is equal to the Galois group of L over alpha of F. Now, now at this point, we want to deduce, to go back to 2, that F is equal to alpha of F. And we can deduce this because we have the fundamental theorem of Galois theory, which tells us that there is a there's a bijection. I mean, we have this bijection between the subgroups of the Galois group and the intermediate fields. So if the subgroups are equal, as they are here, then the intermediate fields are equal. So by fundamental theorem, so I mean, not isomorphic, but equal as subgroups. No? By the fundamental theorem of Galois theory, we have that f is equal to alpha. And you know, for all alpha in the Galois. Now we want to deduce from this that the field f is normal over k. So we have to find that, you know, the minimum polynomial for any element splits or something. Let small f be a polynomial with coefficient in the ground field k with a root a in f. Then, in order to see, we have to show that f splits over f. Yeah, that's always the problem if you use the same letters over the field f. So we know that f splits over L because L over K is a Galois extension. So we have to show that any root of f in L actually lies in F. So let B in L be a root of F. We have to show that B is in our field F. What?
I say in F.
Yeah. Yeah, I don't know what's I don't know what's wrong with me, but on the other hand. Yeah, no, this was F, yeah. Okay.
In F.
Yeah. Let B be a root, so let B and L be a root of F. And now we want to show that B lies in the field F. So, but both A and B have the same minimal polynomial over K. So we can assume that F was monic, by normalizing it. Yeah, so here obviously was not careful. So I want this to be f in kx be irreducible. So that's what you need for now. So they have the same polynomial over k, namely f. So thus there exists an element in the Galois group which sends A to B. Thus, no, we had this theorem that there exists an element in the Galois group sending one element to the other in the Galois extension if and only if they have the same minimum polynomial. So thus there exists an element, say alpha, in the Galois group of L over K with alpha of A is equal to B. So, but you know, we have that f is equal to alpha of f for every alpha. So, as f is equal to alpha f, we get B is an element in F. And so the extension was no. Okay, so this is So this is not so, I mean, in some sense, okay, here one has to be a little bit careful, but in some sense it's similar arguments that we have used before. We just use them carefully. Now, obviously, we can also ask ourselves another question. Now, we know now if the Galois group of L over F is a normal subgroup, of the Galois group of L over K, then F over K is a normal extension So one thing we can ask ourselves, what is the Galois group of this extension? Somehow we should be able to express it in terms of these two. No, one would hope. So what could be the answer? So this group is a normal subgroup of this group, and we want to make another group out of these two. Yeah. So the natural thing we want to do is to take the quotient, and so we claim that this is the case. So we have this Galois extension, and F over K intermediate field is so F intermediate field with F over K normal. Then we have a subset canonical isomorphism. The Galois group of F over K is isomorphic to the Galois group of L over K, divided by the Galois group of L over F. Okay. No, somehow. Okay, and so that's actually quite simple, because if we have an element in the Galois group of L over K, we know that it sends F to F, so it gives us an element in the Galois group of F over K. And so we have a natural map from the Galois group of L over K to the Galois group of F over K, and the claim is that it's surjective and the kernel is this. Okay, let's do it. So let alpha be an element in the Galois group of L over K. So then, as I said, alpha of F is equal to F. Thus, if I take alpha restricted to F, from F to F, this is an element in the Galois group of F over K. Because it's an automorphism of K, of F, and still the identity on K. So thus we have the restriction map which is kind of restriction to F from the Galois group of F over K to the Galois group of F over K. So this is obviously a group homomorphism, no? Because before it was a composition, afterwards a composition is a group homomorphism. And essentially, by definition, its kernel is the Galois group of L over F. is, what is it? This is the set of all alpha in the Galois group of L over K, such that alpha restricted to F is the identity, which is by definition equal to the Galois group of F over F. So we know that this is the kernel, so therefore we get an isomorphism of the quotient of this divided by this to the image of the map. We want it to be this, so we want to show it surjective. So to show this restriction to F. Over K is surjective. And this is also, I think, relatively obvious. Yeah. So in this case, we just can look at the number of elements. So the number so maybe I should have said this. So the kernel is this. So thus we get an injective homomorphism from the Galois group of L over K divided by the Galois group of F over K of L over F. So the Galois group of F over K, and we want to show it's also surjective. But we can just look at how many elements they have. So that on both sides we have the same number of elements, then it's fine. So the order of this quotient, the Galois group of L over K, divided by the Galois group of L over F, this is the same as the degree. So these are both Galois extensions, so the number of elements in the Galois group is equal to the degree of field extension. So this is L over K divided by L over F. And by the degree theorem, this is just the degree of F over K. And as this is a normal extension here, this is the Galois group of F over K. Number of elements in the Galois group of F over K. Because this is also. And so we therefore see that these two sides have the same number of elements, so this injective map must be surjective. Okay. Let's briefly look at some couple of examples of this correspondence to see, how the subgroups correspond to the intermediate field. So just two examples of field extension, of Galois extensions that we have looked at. So the first example was this, we take Q, third root of 2, and say e to the 2 pi I divided by 3. This was the splitting field of x to the third minus 2 over q. So maybe to save some energy, some have it less difficult, I call this A, and I call this omega. So we know that, the Galois group of this field extension over Q, that this is isomorphic, or I just say equal to S3, where this is the group of all permutations of all the roots. So group of permutations of all the roots of this polynomial. So of roots, say A. So the first I number them. A1 is equal to A. A2 is equal to A times omega. A3 is equal to A omega squared. And then, so if I just say permutation 1, 2 is the one which permutes these two and so on. So we know that this is the Algebra group. And so we can write down the diagram of all the subgroups and the corresponding diagram of all the intermediate fields. So the subgroups so I write kind of, I start with the smallest. If I connect things with a line, then the one above is contained as a subgroup in the bigger one. So we have here 1. This is contained in the subgroup generated by the transposition 1, 2, transposition 1, 3, say, and the transposition 1, 2, 3. And there's one more element, namely this one more subgroup, which is this cyclic thing, 1, 2, 3. Okay. So these are transpositions. So this group has 2 elements, this subgroup has 2 elements, this has 2, and this has 3. So these are the cyclic, the 3 cycles. And all of them are contained in S3. So this is the diagram of subgroups. And now we want to look at the corresponding, we should have a precisely corresponding diagram of fields. So the field corresponding to the trivial group is the whole. No, that we know it's a fixed field of the identity. There is the whole field. So now, what is it if we permute these two? So we want to permute A1 and A2 and let A3 fixed. So what is an element which is fixed by this? Obviously A3. So the first guess, so certainly we must have that if I take Q A omega squared, this will be, this is contained in the fixed, this is certainly fixed. We only have to see that this has the correct, that this is the correct field, I mean has the correct degree, but you can easily see that the degree of this over, so here this S3 corresponds to Q, and this is the root of a cubic polynomial, so the degree here is 3, as it should be, because the index is, we get to have here the index of this subgroup here is 3, and so this is 3. And so this is right. And so obviously by the same token, if we permute, if we exchange 1 and 3 and leave the second one fixed, we get Q A omega. So here obviously the inclusion is the other round, so this is a subfield of this is a subfield of this. So I can also here write, so maybe I can say what the index always is. So the 1 is contained here, so this is 2, 2, 2, 3, and this is 3, 3, 3, 2. So this is the index of the corresponding subgroup. And so the degree of the field extension here is here 2 and here 3 in the same way, as the theorem says. Then here we've got obviously QA. And finally, if we permute these three cyclically, so A1 goes to A2, A2 goes to A3, A3 goes to A, what element would be fixed by that? Hmm? Yes, but okay, one could do that. Not precisely sure. Yeah, no, that's however not very useful, because if you think of it, if you take 1 plus omega squared, this is equal to 0. So if you take the sum, this is 0. So this doesn't actually help. But anyway, it certainly was a possible idea. But one other thing we can do, we can always divide one by the next. So if we take, or by the previous, if we take a omega and divide by a, we get omega. If we take a omega squared and divide it by omega, we get omega. And omega to the third is equal to 1. So if we take a and divide by omega squared, we get omega. So if you permute them cyclically, this thing will stay fixed. I mean, the quotient between always one and the next is fixed by this operation. No? So we have a2 by a1 is equal to omega, is equal to a3 by a2, and also a1 by a3 equal to omega. So always the quotient of 1 by the one before is just omega. And if we permute them cyclically, so just shift everything further, it's still true, and the quotient of 1 on the next is always the same, omega. So we can take here q omega. And now we know that, again, omega is this, this is the zero polynomial of degree 2, namely we have the minimal polynomial would be x squared plus x plus 1. No? And so the degree here over q is 2, and so therefore the degree is 3. So it is the correct thing. So we see that this diagram of subgroups corresponds to this diagram here. We can also, obviously I'm going a bit, it's not, so let's look at the other example that we had. The other example is this, in this case, we had an f equal to x to the 4 plus 1, and the splitting field, we take the splitting field of this, over q, which we write as q alpha, where we can take alpha equal to e, what is it, to the 2 pi I over 8, or pi I divided by 4, or if you want, square root of I. And then we know that over q alpha this splits. We have that f is equal to x minus alpha times x plus alpha times x minus 1 over alpha times x plus 1. And we also had seen that the Galois group of f, which is the Galois group of q alpha over q, is isomorphic to C4, C mod 2z, C mod 2z plus C mod 2z, it's not cyclic. Namely, and this isomorphism is in fact this one is generated, so the elements are just, so this here is generated by alpha goes to minus alpha, and this one is generated by alpha goes to 1 over alpha. So this is what we had seen. So we have then the four elements are, what do I want to say it? So this thing in this identification, I call this element, I call 1, 0, so it's the 1 here and the 0 here. This one is 0, 1, and alpha, the identity obviously is equal to 0, 0, and the alpha goes to minus 1 over alpha would be identified here with 1, 1 in this picture. So I just write like this so that we identify this with the Z2 term Z2. Here it's additive, and so the sum, which means product of these two, is just this, so composing. Okay, now we can look at the corresponding diagram. So this is an abelian group, so it's very easy to see what the subgroups are. It's just the subgroup generated by, so we just have the following, we have here the identity element generated by it, then the subgroup generated by 1, 0, so that by 0, 1, and that by 1, 1, and then we have the whole group. So these are all the subgroups and these are all the inclusions. So what are the corresponding intermediate fields? So we know that the identity element, so it's always, this corresponds, a subgroup corresponds to the corresponding fixed field. So the identity element fixes everything, so we get the diagram of fields, so here we get Q alpha. We know that the whole subgroup fixes only the ground field, so this is Q. Now we have to find the intermediate fields. So let's look first at alpha. So if we take the element 1, 0, this was, according to what I said, alpha goes to minus alpha. You have to find, some elements which are fixed by that. You have to find the fixed field of that. So it's maybe you just try to find one element fixed by it. So what could that be? So if we send alpha to minus alpha, what would be fixed by that? So yeah. So I mean, so one thing is that minus times minus is plus, and so you could have alpha squared is certainly fixed by it. So we could hope that this is Q of alpha squared. And remember that alpha is equal to the square, could be viewed as the square root of I. So alpha squared is equal to I. So I could also say this is Q I. And this certainly has degree 2 over this, as it should, because the index here is 2. And so this is fine. Now the other ones are a little bit more tricky. So now we want to say alpha, so we take the element 0, 1, which means alpha goes to 1 over alpha. What is fixed by that? Maybe, for instance, you could try again what you tried before. Well, because this time it seems to be a good idea. So you said you should take the sum of the things. So in this case, so why don't we take alpha plus 1 over alpha? So I want to say, so we know that the fixed field contains Q alpha plus 1 over alpha. Because Q is fixed and alpha plus 1 over alpha is fixed if we send alpha to 1 over alpha. Now maybe we can make it also more explicit. So if we have here, if we look at the complex line, we have here square root of I. So this is square root of I. So 1 over alpha is this one. So this is alpha, 1 over alpha. This is e to the pi I divided by 4, e to the minus pi I divided by 4. And so we have this. And what's the sum? We put we make the corresponding parallelogram like one does in physics. So this is this plus this. This is we have this is a square, and so this thing is just square root of 2. So therefore this is the same as q square root of 2. And again, so we see the degree of this over this is 2 as the index of the subgroup, so that's fine. And well, now it's not so. So here the element 1, 1 is alpha goes to minus 1 over alpha. So obviously, as the trick worked before, so we say that now the fixed field will be alpha minus 1 over alpha. So we take the q alpha minus 1 over alpha. And here we can also make a drawing. So here was our alpha. Now, here's 1 over alpha. We take minus that. And so again, we have a square here. I mean, although it doesn't look like it. And so this will be I times square root of 2. Again, we can see that, so the minimal polynomial of this is x squared plus 2, so the degree is 2. And so we have again, this is a degree 2 extension. And this is the complete picture. You can see, I mean, it's not, I mean, there might be different ways how to see these things, but you see, it's not particularly difficult, but it's also not completely trivial. I mean, you always have to think a little bit, no, and somehow try to figure out what is happening. So the way I always did here is that I find some intermediate field which is fixed by the corresponding group, and then by just looking at what the degrees are, one sees that it is already the whole thing. No? Because if the fact that you have a field which is fixed by the group doesn't mean it's the fixed field. It could be that the fixed field is larger. But if the degrees are the same as the corresponding indices here, then it is fine. Okay, so these were these examples. So I was a bit slower than I thought. So I wanted to make some other remark, which I think you most likely already know, but just for the practical to know. Some sense another example. It's just if we work so just about complex conjugation. So assume if we take polynomial f, say with coefficients in q or something, and k inside C is its splitting field, then we can always look at the complex conjugation. So we take I, say iota, from C to C, which sends A plus IB to A minus IB, and complex conjugation. So I claim that this will always be an element in the Gottshe group of K over Q, so in the Gottshe group of F. And then this iota, if I restrict it to K, obviously, and restrict it to K, from K to K, is an element in the Gottshe group of K over Q. derivative of f. It's actually more or less. So mostly we just have to see that it sends k to k, but that's kind of obvious because we have assumed that the coefficients of f were in q, so in particular they're in r. So first, iota maps k to k. So we have that, we had this map over star. So which means, so you remember we had that this map, if you have a polynomial f equals some ai x to the I, like our given one, and then we had defined, and iota is some field homomorphism. We can, maybe of some bigger field, we can apply this thing to this polynomial. So then iota star of f was defined as the sum I equal over all I iota of ai x to the I. And obviously for our f, this is equal to f because the ai are in q, and so certain complex conjugations are equal to that. So thus, if alpha is a root of f in k, then iota of alpha is also a root. And as we have assumed that this is the splitting field, it follows that iota of alpha is also in K. So we therefore see that it maps, so this is true, so as K, as K is generated as a field over Q by the roots of F, because it's the splitting field, it follows that iota maps K to K. And obviously, this is this original K was an isomorphism. This original iota was an isomorphism, so its restriction is also an isomorphism. So it's an element. It's an isomorphism from K to itself, which is by definition the identity on Q. So thus, iota is an element in the grammar of K over Q. So if we have such field extension, the complex conjugation is always this, and this leads to something that you already, I think, know from maybe from high school or something, namely that the complex roots of the real or rational polynomial always come in pairs of complex conjugated roots. So, so if alpha is a 0 of our given f in K which does not lie in the real numbers, then if we take alpha bar, which is the complex conjugate, is different from alpha, and it's also a root of f. So thus the non-real zeros of f come in pairs of complex conjugate. So in particular, you see, for instance, if you have a polynomial of, this also obviously follows from analysis, but if you have a polynomial of odd degree, then it has, it has to have an even number of complex roots, so it has an odd number of real roots, and in particular, it must have a real root. Okay, so now, still a little bit of time. So now, I want to briefly, maybe I have time to do this, briefly talk about the Gottshe group of the Gottshe theory of cubic polynomials. It's not just very simple, and then next time we will start with one of the somehow the main motivating problem motivating the Gottshe theory, which is the solution of polynomials by radicals. But let's first look at this. So what is it here? So if f equal to x to the third plus a x squared plus bx plus c is, say, an irreducible polynomial of degree 3, but it also says cubic, say over q, 1 over some field k for a moment. Then we can simplify it a little bit by getting rid of this coefficient. So we put the y equal to x minus a divided by 3, then this gives f is equal to x to 3, say plus px plus q, where you can compute what p and q is. No, just if you, now obviously it's not x now, y, but that's still a variable. No, you just compute, obviously this coefficient goes away if you do this. If you understand this polynomial, you understand this by this, because you just have made this stupid shift. So no one can study the second. So now we want to briefly understand. So assume this polynomial is, we have assumed this is irreducible. So we want to know what are the possibilities for the Gottshe groups. So what are the possibilities for the Gottshe group of f? Maybe for simplicity, I can just assume it's q, it doesn't make a difference, and then I don't get confused. So the Gottshe group of f over q. So let's look at it. So what can happen here? So we assumed it's irreducible. So let L be the splitting field. L of our polynomial f over q. Maybe if you wish, you can assume it as a subfield of the complex numbers. So then we can write f is equal to x minus alpha 1, x minus alpha 2 times x minus alpha 3, where the alpha I are elements in F. No, these are the roots of it in the splitting. And we have made this assumption that looks like this. So this in particular means that the sum of the roots is up to sine the coefficient of y squared. So alpha 1 plus alpha 2 plus alpha 3 is equal to 0. Then the quadratic, this term here is the sum of the squares. So alpha 1, alpha 2 plus alpha 1, alpha 3 plus alpha 2, alpha 3 is equal to p. And if I take the product of all the roots, that's minus the constant coefficient. So alpha 1, alpha 2, alpha 3 is equal to minus p. So now we want to understand what can the Galois group be and how can we see what the Galois group is by just looking at the polynomial. So clearly alpha 3 lies in Q alpha 1, alpha 2 because the sum of the 3 is 0. So we have to at most add 2. So we have therefore Q is contained in some intermediate field F, which is Q alpha 1. And this will be contained in Q alpha 1, alpha 2, which is our L. Now, as F is irreducible, we have that the degree of F over Q is equal to 3. So we have, the first extension has degree 3. And now there are obviously two possibilities. Either these two are equal or they're not. Now, two possibilities. First, F is equal to L, or F is strictly contained in F. Now, as this polynomial f has degree 3, so let me first see. So first, if f is equal to L, then the Galois group of L over K is, now we have a simple algebraic extension, so this is a subgroup of the permutation of the three roots, which acts simply transitively. So I mean, I just say of S3, acting on the roots. And simply transitively. So I have just I viewed a subgroup of S3 via its action on these things. So what are the subgroups which act simply of S3 which act simply transitively? We know what the subgroup of S3 are. We have written them on the blackboard. There's only one which does this, namely the cyclic permutations. So thus the Galois group of L over K must be equal to the subgroup of the cyclic permutations. No, which one can, okay, which is also equal to the alternating group, so the group of even permutations. No, because you have the subgroups are only the one generated by one transposition, which obviously does not act transitively, or the whole group, which obviously does not act simply transitively. Okay, so we have this. So this has no non-trivial subgroup. Well, it's also clear anyway. So no intermediate field. Between L and Q. Now let's look at the other case. Okay. I think I want to start slightly late. So if F is strictly contained in L, then as we know, then we know that the Gottshe group of L over K is equal, the number of elements is equal to the degree of the field extension. In the first step, the degree already was 3. So if it's bigger, it must be a multiple of that. So it must be at least 6. So that means it must be the whole of the symmetric group. So then the Gottshe group of L of F over K, of L over K is naturally isomorphic to S3, so the full symmetric group commuting all the roots. And now, how can we now want to see? and in this case, we do have some intermediate fields, obviously. I mean, we have this intermediate field here, F in the extension. So how can we decide which of the two? How do we see which of these is true for F? So now I write it in the P and Q, x to the 3 minus plus P x plus Q. So one can see this in terms of the discriminant. What is that? So we can just write down. So definition, just the definition of discriminant is so what is it? D, I take the difference, the squares of all the differences of two groups. So this is alpha 1 minus alpha 2 squared, alpha 1 minus alpha 3 squared, alpha 2 minus alpha 3 squared. Now, what? Yeah, obviously the square was here. Otherwise it would be somewhat strange. And now this is equal, as you can check after the somewhat. So remember that I had said what the relation between the alpha i's and the P and Q is. So I claim that this is equal to minus 4 P to the 3 minus 27 Q squared. This you can check after a longish calculation. Okay, so this is some calculation. So obviously if we have the polynomial, we can compute this number. And now the claim is, only preposition. That is not strong. Anyway, the Galois group of my field extension for this L of k given by f is contained in A3, which is our situation here. So we have a degree 3 field extension if and only if D is a square in Q. So if this number is a square of a rational number, then this Galois group is this. So we can see we have written here this as a square, but it's a square of these roots which lie in one square. But anyway, this is the thing. And so therefore you have a very simple criterion to check. So you write down the polynomial, you compute this, and you can see which of the two is true. And why is this the case? So let sigma be an element in S3. And now I view this as acting on the roots alpha 1, alpha 2, alpha 3. Also the transposition 1, 2 will exchange alpha 1 and alpha 2 and so on. So then I can put delta to be one choice of the square root of D, which I just take to be just the product of them without the square. Obviously there would be other choices with signs, but I say choose this one. So what does sigma do to this element? Then if I apply sigma to this element delta, what do I get? Whenever, so remember that this, whenever I apply a transposition to two elements, one of these things changes signs. If I if I take the transposition 1, 2, alpha 1 minus alpha 2 becomes alpha 2 minus alpha 1. And and the other ones don't. So we see that sigma of delta is just equal to minus 1 to the k times delta, where k is equal to the number, also the number of pairs I smaller than j between 1 and 3, such that sigma of I is bigger than sigma of j. So it's change order. This is nothing else than the sign of the permutation times delta. So thus this element, so we know that delta so thus delta is an element in Q, which is equivalent to saying that D is a square in Q if and only if, if and only if it's fixed by the Galois group of L over K. So, because this is L over K is a Galois extension, so the fixed field of the whole Galois group is L over Q is a Galois extension, so the fixed field of the Galois group is Q. So if and only if sigma of delta is equal to delta for all sigma in the Galois group of L over Q, which is if and only if all elements in the Galois group are even permutations. Okay. So this was the stupid. I'm sorry, I went a bit longer than I thought. So anyway, I mean, it's maybe not such an important thing, but it's kind of funny that you can kind of read off such a thing directly from the coefficients. You can also see, I mean, something more obvious which you can see from this thing is obviously that this thing, the discriminant, will be 0 if and only if the polynomial has a double root. No? And that's clear. And something which is more complicated, which I think you can also see some. Yeah, anyway. I think one can also see something about whether or not all the roots are real or not from the sign of the discriminant. But this I do not. Okay, maybe that's enough for now. So.